8.4 is the last section that we're going to tackle out of Chapter 8. And we're going to talk about vectors. Now, vectors are something you see a lot more in your physics classes. When you're talking about a vector, you're talking about directed motion. A vector has both magnitude and direction. From a geometric point of view, vectors are represented by directed line segments, where the length of the directed line segment is the magnitude, and the direction is from P to Q in this example. So we have an initial point and a terminal point, and we know which direction we're going because of the arrow. The vectors below are equal because they have the same magnitude, the same length, and the same direction. Notice that where you start and where you stop on the graph does not define the equality of the vector. If I wanted to compare these three vectors, I would say that for P, I go to the right and up. I travel to the right 1, 2, 3, 4 units, and then I go up 3 units. For this vector, I go to the right 4, up 3, to the right 4, up 3. So each of these is builds on an equal right angle, so they are going to be the same distance, the same direction. Vectors are denoted with a bold character, which you can't really do by hand, or written with an arrow over the top of the letter. For example, in this graph, we've got vector V, so they can write it as a bold-faced V, or we can just do V with an arrow on top to designate that it's a vector. If I want to add vectors, for example, if I'm going to add V and W, draw vector V, and from the terminal point of V, so where V stops, I'm going to connect the initial point of W. The sum of these vectors is the vector whose initial point is V and terminal point is W. So if I'm adding V plus W, I sketch them so that one follows the other, and then the sum V plus W is this line that connects from my starting to my final termination point. Now we are going to skip a couple of things in this note section. The first thing we're going to skip is this exploration. You're welcome to do that. It's excellent, but I feel that it is unnecessary. So we're just going to fill in our definitions for some properties that vectors do follow. Vector addition is commutative. That means that if V and W are any two vectors, then V plus W is the same thing as W plus V. Just like our regular integer addition is commutative. 2 plus 3 is 5, 3 plus 2 is also 5. Vector addition is also associative. So order doesn't matter here, and grouping doesn't matter here. If I'm adding 3 vectors together, it named W twice, rename that as a U, VW and U. If I start by grouping together W and U, I can change that grouping and I get the same result. The 0 vector is just like our 0 with addition. So that V plus 0 or 0 plus V is just V. It doesn't change anything. If V is a vector and negative V is a vector of the same magnitude, it goes in the opposite direction. So therefore, V plus a negative V gets us to 0 because they cancel each other out. This allows us to rewrite the difference of two vectors, V minus W. If I start with V minus W, I can think of it as V plus a negative W, the opposite of W. So instead of doing subtraction, I can think about the opposite of addition. Now what about multiplying vectors? If I want to multiply a vector times a scalar, or basically just an integer, and I have the scalar alpha. So my scalar is a real number, and v is a vector. The scalar multiple alpha v is defined, and there's another typo. I wish I could get all these out for us. Alpha v is defined as, okay, as long as my scalar is positive, then the product is the vector whose magnitude is alpha times the magnitude of the original vector, and the direction is the same. If, however, alpha is negative, if it's less than 0, then that product vector has a magnitude that is alpha times the vector that goes in the opposite direction as our original vector. And if our scalar is just 0, then when I multiply anything times 0, I get 0. So think about what we just said. Now, our vector multiplication, addition, subtraction follows what we're used to with our real number arithmetic. So that's not so bad. It's kind of noisy here because the trash truck's here, of course. Okay, anything times 0, so this is practice. Anything times 0 is 0. Anything times 1 is itself. Anything times -1 for a vector changes the direction. Remember that. So if I went up and to the right, now I would go down and to the left. Here I'm going to distribute so that I have alpha times the vector plus beta times the vector. Here I'm distributing in the scalar. So alpha v plus alpha w. And here I'm multiplying two scalars together, so alpha beta times the vector. Okay, we're going to graph these vectors. You're going to need a sheet of graph paper. Hopefully I included that with your guided notes. If I failed to do that, pause the video and go just print off a sheet of graph paper. Now these are the three vectors that we have defined to use. This is vector v, vector w, and vector u. Notice that they all have magnitude and direction. V is going to the left and up, left 3, up 2. W goes down 2, right 2, to the right. Oh my goodness, long day. To the right 3, up 2, down 2, right 2, and right 1, up 2. Up 3, can't count either, up 3. Okay, so let's just do this. We're going to start by taking 2 times v and subtracting from it w. And remember that I can think of that as 2 times v plus the opposite of w. So for w, instead of going down and to the right, the opposite of w is going to go up and to the left. Alright, 2 times v. So let's start with that. This is 1a, and we're going to start with 2 times v. Well, v goes 1, 2, 3 to the right and 2 up. We need to do twice that. So for 2 times v, I'm going to go 6 to the right and 4 up. So I'm going to give myself some space. This will be my initial point. So I'll go 1, 2, 3, 4, 5, 6 to the right and 1, 2, 3, 4 up. This is where 2v will terminate. So there is 2v. Now I need to do the opposite of w. Well, w goes down 2, right 2. So the opposite of w from this terminal point is going to go up 2, left 2. So up 2, left 2 means that the opposite of w is going to terminate there. The vector that I'm interested in, therefore, starts where the whole thing started and ends where the whole thing ends. So this is 2v minus w. That's my solution. Vector, vector. All right. That is vector v, that is vector w. Let's look at the second example. So we've got 1b is, I take vector v and I subtract 2 times vector w. So that's going to be the same thing as the opposite of 2 times w here. But I'm going to start with vector v. Again, vector v is right 3, up 2. So I'm going to pick a starting place and I'm going to go right 3 and up 2. That is v. Now I'm going to do the opposite of 2 times w. So instead of 2 and 2, I'm going to go 4 and 4. Instead of down and right, I'm going to go up and left. So from the place I stopped, I'm going to go up 1, 2, 3, 4, and to the left 1, 2, 3, 4. And that is a negative 2w. My result starts at the initial point where I started and finishes at that point where I finally stopped. This is v minus 2w. That's my goal. That's what I was after. Okay, my third example, C, is right here. V plus 2w minus u. Vector v plus 2 times w minus vector u. Alright, let's take plenty of space. So I'm going to start kind of down here in the middle. Vector v goes right 3 up 2. That's what I'm going to start with. I'll start right here and I'll go right 3, 1, 2, 3, up 2. That is where I stop with v. Next I'm going to go a positive 2w. So w goes down 2, right 2. Twice that is down 4, right 4. So from my terminal spot, I go 1, 2, 3, 4 down and 1, 2, 3, 4 over. So that is where 2w will terminate. Now, finally, I need to do the opposite of u. Well, u goes right 1, up 3. So the opposite of that will be left 1, down 3. So from this stopping place, I go left 1 and down 1, 2, 3, and that is where the opposite of u lands. So from my very beginning point to my, and I got to get this where I can see my line, my very beginning point to my final end point, point of termination, this is vector v plus 2 times vector w minus vector u. That's this vector right here. Okay, let's start talking about the magnitudes of vectors. This symbol represents the magnitude of vector v. So it's like a double absolute value bar. If v is a vector and alpha is a scalar, then the magnitude of v is going to be greater than or equal to 0. And we know this because distance is non-negative. Magnitude is distance, it's non-negative. The magnitude of v is 0 if and only if the vector is equal to 0. And the magnitude of a negative v is going to be the same as the magnitude of v because it's always going to be positive. The magnitude of alpha v is going to be the absolute value of that alpha, that scalar, times the magnitude of our original vector. A vector u, for which the magnitude of u is 1, is called our unit vector. So there is a new definition for us. We haven't talked about a unit vector. Alright, a position vector. An algebraic way of representing vectors by using components is by using components in a position vector. Now this is basically what I was doing when I was counting over and up or over and down, doing a horizontal and then a vertical. I was using components, we just didn't discuss them as components. So an algebraic vector is represented as v equals the components ab, and notice the little kind of pointy parentheses there, where a and b are real numbers, scalars, called the components of vector v. If the component's initial point is at the origin, and the terminal point is at coordinates AB, then v is called a position vector because the initial point is at the origin. A position vector describes the horizontal and vertical movement of the directed line segment from the initial point. Find the position of vector v if the first point is at negative 3, 1. So my starting place is at negative 3, 1, P1, and my ending place is at 6, 3. So 6, 3, that's P2. Plot the points, so we did that. Initial point, terminal point, that's number 1, got ahead of myself. Now, from the initial point to the terminal point, determine the horizontal and vertical movement. So to get from here to there, I would go horizontally 9 units and vertically 2 units. Because I had 6 minus a negative 3 on the x-axis, and I had 3 minus 1 on the y-axis, if I'm looking at the coordinates. This answer is the position vector, because if the initial point was at the origin, the horizontal and vertical movements that we applied, the two vectors would have the same magnitude and direction. Okay, here's our theorem. Suppose that v is a vector with an initial point at x sub 1, y sub 1, not necessarily the origin, and the terminal point at x sub 2, y sub 2. If that vector is p sub 1, p sub 2, then v is equal to the position vector. We find the distance along the horizontal that we shifted and the distance along the vertical that we shifted. That gives us the components for our vector. Okay, the results from part 3 of our exploration 3 can be summarized here. Two vectors v and w are equal if and only if their corresponding components are equal. So if a sub 1, b sub 1 are the components for the first vector v, and if w has a sub 2, b sub 2, then the two vectors are equal if and only if the a components are the same and the b components are the same. So let's think about this algebraically using unit vectors. So here is I. Its components are 1, 0. I've gone horizontally 1, vertically 0. Here is j. The components are 0, 1. I've moved horizontally 0, vertically 1. Therefore, vector AB, where A is 1, 0 and B is 0, 1, A, if distribute here, is just AI, and B is B times J, because we have I here and J there. Don't stress about that, okay? For an example, if I have vector v, the components are 5, 4, I can, oops, that should be a pointy, there we go. I can express that as 5i plus 4j. 5 on the horizontal, 4 on the vertical. Adding and subtracting vectors algebraically. This gets us all in one place so that you know what to expect if you're adding, subtracting, multiplying, or finding the modulus of a vector. If I'm adding v plus w, to get the I component, I would say a sub 1 plus a sub 2 I, plus, in the j component, b sub 1 plus b sub 2 j, and that's going to be a1 plus a2 is my first component, b1 plus b2 is my second component. Now we're going to work out examples of these, so don't stress about it right now. Just get it down in your notes, and then we will do the examples on the next page, and it should start falling into place. This is really not a complicated arithmetic for you. For subtracting the vectors, instead of adding, I'm just subtracting those same values. So a sub 1 minus a sub 2i plus b sub 1 minus b sub 2j is the same thing as a sub 1 minus a sub 2, b sub 1 minus b sub 2 in those component positions. What if I want to multiply by a scalar? Well, then I have alpha ai, or a sub 1 times I, plus alpha b sub 1 times j is going to equal to alpha a, alpha b. Now, to find the magnitude of the vector, we are going to do something a little different. We're going to take the square root of the sum of the squares. Square root of the sum of the squares. But that shouldn't surprise you because that's what we've done for that modulus for the, all the way through. And then it gives you some graphs to illustrate these definitions. You're welcome to look through that. We're not going to take the time as part of our video. I'm going to go ahead and get through the rest of our arithmetic here. Okay, so we are going to add and subtract vectors algebraically using those component parts. Basically, what we were saying was we were going to add the similar components. So where v is 6i minus 2j, that means the component form is 6, negative 2. W is 2i plus 5j, the component form is 2, 5. We want to find v plus w, vector v plus vector w. Well, I add the first component parts, so that's going to be 6 and 2. And I add the next component part, so that's negative 2 and 5. So that gives me 8i plus 3j, and when I write that in component form, it's 8, 3, with the little pointy brackets. Okay? Now subtracting. Again, I subtract that first component, so 6 minus 2, and that's my I, and then I'm going to combine with that the negative 2 minus 5, and that's my j. So that gives me 4i plus a negative 7j, or 4 minus 7 in my component form. Okay, multiplying by a scalar, we're going to multiply 5. So v is 6i minus 2j. So when I multiply those by 5, I get 30i minus 10j, or in component form, 30, negative 10. On b, I'm going to multiply 3 times v, 2 times w, and then subtract. So if I multiply 3 times v, that's going to give me 6 times 3 is 18i, and then minus 6j, and I want to subtract from that 2 times w, so that's 4i and 10j. So that gives me 18 minus 4 is 14i, and negative 6 minus 10 is a negative 16j, and I write that in the correct form. And finally, I'm asked to find the magnitude of vector v. Remember, I take the square root of the square of the first plus the square of the second. That gives me square root of 36 plus 4, which is square root of 40, which would simplify to be 2 square roots of 10. Alright, finding a unit vector is actually the last thing we're going to do. Recall that a vector u, for which my magnitude is 1, is called the unit vector. Just like a unit price at the grocery store can be found by taking the price of an item and dividing it by the number of units. For example, if you're trying to figure out which can of tuna is the cheapest, you're going to figure out the small one or the big one. You figure out the price per ounce. You don't necessarily look at the price per can. That gives you a unit price. The unit vector can be found by taking the vector and dividing it by its magnitude. For any non-zero vector v, the vector u, the unit vector, is v over its magnitude. Another way to say this, to rearrange the terms, would be v is equal to u times the magnitude. Alright, let's find that unit vector that's like a unit price. And again, we're just going to stop right here. Okay, Finding a unit vector in the same direction, find a unit vector in the same direction as v equals 12i minus 5j. How can you confirm your answer is correct? Well, the first thing I need to do to find the unit vector, because the unit vector is the vector over the magnitude, I need to find that magnitude. So, magnitude of v is square root of 12 squared plus negative 5 squared, which gives me square root of 169, which is 13. 13, there we go. So where I have the unit vector is the vector over the magnitude, that gives me 12i minus 5j over 13, which is the same thing as 12/13 I minus 5/13 j. Now it wants me to check it. Well, to check it, I would just need to square the two components and see if I get 1. So if I do 12/13 squared, this is my check. If I do 12/13 squared plus negative 5/13 squared, do I get 1? 12/13 squared is 144 over 169 plus 25 over 169. Yes, that does give me 1, so it checks.